Hi guys, in this video I'm going to cover change of variables and integrals, which in the context of statistics is also related to transformation of continuous random variables and to reparameterization of parameters in Bayesian inference, among other things. Even though this topic is basic, I feel that, at least for me, it's also very tricky and slippery. So I wanted to understand it better. There is more depth that you can go into, for example, with measure theory, but I think this depth is good enough for me, and I hope you find it also useful. Change of variables is usually learned in calculus. It's a way to simplify otherwise hard integrals, and sometimes it's also the only way to solve hard integral analytically. It is also important in statistics, for example, when you change random variables into a transformation of random variables, or in the Bayesian inference when you reparameterize your parameter space, and it easily gets you the new PDF of your new variables. So what is the problem? Let's look at the 1D case. So suppose you have this integral, and this integral might be really hard, but you might notice that you actually can write it differently. Maybe you can write it as a function of x, where f is more easy to integrate. So you decide to do a change of variables. You introduce a new variable and you call g of x u. So basically you moved from, let's say, h of x to f of u. Now the way to do this involves 3 steps. Step 1 is changing the variable in the function, so changing all the x's to u's. Step 2 is correcting the integration units using the Jacobians, and this is the thing what we will go into more in depth. But for now, just remember that in the 1D case, d of u will be equal to g prime times dx, where g prime is equal to du dx. Okay, so the derivative of u, which is our new variable, which is a function of x, it's g of x with respect to x. And then the step 3 that you have to take care of is the limit of integration. You have to change them in definite integrals. So let's see an example. Suppose we want to find the indefinite integral or the antiderivative of this expression over here. So one way to do this is to say, okay, let's call half of x squared u. Okay, and then we can, in step 1, we have to change all the variables in the function. So we get e to the power of u, but then x, how do we represent that in u? So we have to see what it is. Well, it's 2u and the square root of that. So this is our new function, f of u. Okay, so we can write this as this. And the second step is changing the unit of integration. So instead of dx, we will have du, and the du will have the derivative of g times dx. The derivative of g with respect to x is just x. And so dx is actually equal to du divided by x, and x we already saw is the square root of 2u. Step 3 is not applicable in this case. And so overall, we get that this thing over here is equal to e to the power of u times square root of 2u divided by square root of 2u times du. These two cancel, and we get this integral. And of course, the integral of e to the power of u is just e to the power u plus some constant. And now we can change back again, e to the power of half x squared plus some constant. So this is a way to find the antiderivative. Let's look at a definite integral. So in a definite integral, we have to take care of the limits of integration. So a will be replaced with some function of a, okay, the u of a, and b will be replaced by the u of b, because we're moving from x to u, and u is g of x. Okay, so let's take a concrete example, x times this expression, and let's say we call u the whole exponent. Then f of u will be e to the power of u times, and then this is how x will be in the form of u. Okay, and the step 2 is to replace du with the derivative. So it's 8x. This derivative is 8x times dx. So dx is du divided by 8 times x, and x is square root of u minus 3 divided by 4. And step 3, now it is applicable. X goes from 0 to 1, but when x is equal to 0, u is equal to 3. And when x is equal to 1, u is equal to 7. So our new limits of integration will be 3 and 7. Okay, so overall, if we take this is equal to, of course, this and this cancels. We only get e to the power of u times 1/8. And we can already solve it here. Integral of e to the power of u is e to the power of u. If we take it from 7 to 3, we just get this thing, which is approximately 134.5. Or we can also go back to the original form and then apply the limit. Yeah, so e to the power of u is equal back to this, and then we go back to the same limits of integration that we had before. So both ways is possible. So the general formula for one dimension is if you decide to call g of x u, then d of u will be g prime of x dx, and then you have to replace all the g of x's with u and this thing over here with d of u. Okay, so this is the general formula. Of course, you can combine step 1 and 2. So I kind of did it artificially where you put u is equal, x is equal to this, and then x is equal to this. But if you combine step 1 and 2, then we see immediately that du is equal to 8x dx, and then x dx, which is what we have here, right? X dx. We want to change that. This is equal to 1/8 du, and so immediately we can move from this thing to this thing. Okay, so the big question is, why do we need to correct for the units? Okay, so the change of variable transformation, it keeps the value of our function equal, but it changes the Riemann sum units. And for example, let's take an example here. Suppose we want to look at the integral of 2x from 0 to 1. And we do some transformation that we say u is equal to 2 of x. We move from this graph over here to this graph over here. Now, if we do the integral here, we see if we just sum up the Riemann sum, well, it will just be the area of this triangle, right? It's 2 times 2 divided by 2, and we will get that this is equal to 2. But of course, this is wrong. The integral here is 1 times 2 divided by 2, so the value of the integral is 1. And why does this happen? Well, so first of all, let's say if we take the point x equals 0.5, then its y value is at 1, right? Its f of x is 1. But if we change it to u, then okay, x 0.5 is equal to 1, and the value at of 1 at the new function, yeah, the new function is just f of u equal u, right? So the value of 1 is just 1. So the mapping is conserving the function value, okay? The function value doesn't change. The only thing that does change is the units of integration. So if we take, say, this unit here, okay, let's take it to be 0.1. The Riemann sum is something like this, right? And remember, integration is just a fancy word for summation. So if we look at the Riemann integral, we can say that we take this stripe over here, or maybe we take this stripe over here, doesn't matter, or anything in between. Okay, what happens to this stripe? Well, it's between 0.5 and 0.6, but this maps to between 1 and 1.2, okay? Because 0.5 in x, u is equal to 2x, so this is 1, and 0.6 times 2 is 1.2. So we get that the area became much bigger. So this area, this unit here got multiplied by 2, and so we need to correct for this, okay? So, okay, for the first thing I hope you understood is that the function value stays the same. So for simplicity, let's take a constant function. Let's take the function 1. Okay, it doesn't matter what we change the variable, the function is always 1. And again, we take the same transformation, u is equal to 2 of x. So we move from here to here, okay? So u is equal to 2x. And of course, we can look at the opposite reverse transformation, x is equal to u divided by 2. But notice that if we move here, then this is where we sum, okay? So if we just don't correct for the change of variable, if we don't correct for the new units, then the sum is wrong. In this case, we will get that the sum is 2. 2 times 1 is 2, but this is wrong. We know that the right sum is 1. So we have to correct for this, okay? Because each unit here is transformed into a unit here. So if we take, for example, this unit here, it is transformed into, to this unit here, okay? And so we need to correct for this, and the correction is given by the opposite transformation. So we have to always look at the opposite transformation, okay? What does the opposite transformation does to our unit of integration? And in this case, it takes our unit and divide it by half. Correction is equal to the derivative. So dx du in this case is equal to half, and this is the correction that we have to do. Okay, so and notice that if we actually do the correction here, we get the right result. Okay, so 3 main points to take from this. The function value doesn't change, it's only the units of integration. We actually have to look at the opposite reverse transformation. Okay, so we don't look at this transformation, we look at this transformation. We look at, this is where we sum, and we look at what are our units here, how do we have to correct them when we move back here. Okay, so this is the correction. And the third thing is that we have to correct for this, and the amount of correction is equal to, well, what happens to a unit here? A unit here gets divided by 2. So how do we measure the transformation? It's just the derivative here with respect to u, which is dx du. Okay. Now, in the context of statistics, if we have a PDF for some random variable, and then we change this to a new function, let's say g of x, a new transformation. So let's say x is a random variable, and we move to y, which is some g of x, then the only thing we need to change in the PDF is to multiply by this absolute value of this derivative, of the derivative of the transformation. Now, you might ask, why absolute value? Well, if the transformation is monotonic decreasing, that is, if the gradient is negative, then the limits of integration will also change, and the 2 minuses will cancel out. So for example, let's say we have a uniform distribution, yeah, fx is equal to 1 between 0 and 1. Okay, so this is the same as saying x is uniform, continuous between 0 and 1. And let's say we take the transformation u is equal to minus x. Du is equal to minus 1 dx, dx is equal to minus du. So this 1 dx, if we take the integral of this, let's say for, this is between 0 and 1, but it's also true for any subsections or any intervals in between. Okay, so when we move, the function doesn't change. We have to correct in step 2 for the new units. We do this, but we have to correct in step 3 for the new limits of integration. So 0 is mapped to 0, but 1 is mapped to minus 1. Okay, so this is what we get, but notice that minus 1 is actually before 0. So if we change it to 0 and minus 1, we have to add a minus, and then the minus and minus cancel, and we are left with, again, this thing over here. So yeah, so this is why we could, from the beginning, take just the absolute value here, and instead of minus 1, use 1, because this is what we will get in the end anyway. And another example, let's say f of x is equal to x divided by 2, and x is between 0 and 2. And of course, you can verify for yourself that the integral of this in the domain is equal to 1. And now let's say, again, we take u is equal to minus of this. Again, du is equal to minus half. Dx is equal to minus 2 du. And again, the limits of integration change. So if x was 0, it's now again 0. But if x was 2, then now it is minus 1. Okay, so if we move from this, which is 1, to this, we have to swap the limits of integration, and the swapping creates a minus, which cancels with this minus, and then we are left with this thing. So the new PDF would actually be 2 of u, and u is between 0 and 1. Okay, so this is our new PDF for u. Okay, this was the 1 dimension example. Let's move to 2 dimension. And before this, let's look at a concrete example, which is polar coordinates. So sometimes it's easier to use polar coordinates, especially if we calculate integrals of circular areas. And what are polar coordinates? Well, it's just instead of describing each point in space by its x and y position, which is called Cartesian representation, we move to a radius and an angle representation. So suppose we have a point and we can describe it by our axes, x and y, but we can also calculate the radius, the distance to that point, and the angle from starting from the x-axis counterclockwise, and this is represented with the theta. And so r is equal by Pythagoras' theorem to the square root of x square plus y square, and theta is equal to the arctangents, tangents minus 1 of y. Yeah, this divided by this, but this is just y and this is x. Okay, and notice the theta always lives between 0 and 2 pi's, where 0 is 0 degrees and 2 pi is 360 degrees. So again, like before, when changing to this new representation, basically doing a change of variables, but this time in 2D, the function value stays the same. So in our new space, we will have the exact corresponding for each point in x, y, we find the point in r theta, and the function value will be the same. But the units, the little rectangles that we will use to calculate in x, y will be different than the units that we take in r theta. So again, for simplicity, let's take that the function itself is equal to some constant, let's say 1, and see what happens to the areas. So suppose we want to find the integral of 1 dx dy over the area x squared plus y squared is less than or equal to 1, which is the unit circle. So again, it involves 3 steps. The first step is changing the variables in the function, but this time it's a constant, so we have nothing to change. Step 2 is correcting for the integration area, and we will see exactly how. And step 3 is taking care of the limits of integration, indefinite integrals. What is the limit of integration here? Well, x squared plus y squared less than or equal to 1 is meaning that r has to be between 0 and 1 because r is the radius, so the distance between 0 and 1. And theta, there is no restriction on it, so it's anywhere in between 0 and 2 pi. So this is how it looks like, okay? So this is how we represent the area in xy plane. Okay, so this is x and this is y, and this is how it will be in the r theta. So suppose now we want to take small units, and of course the function is above this. This is 2D, so we have this is the space where of x and y, and the function is above this, and we want to calculate the volume under this. But in this case, the function is constant and it's equal to 1. In 2D, we divide the area into small rectangles. Okay, so if we move from the xy to r theta, what will be our new rectangle? So suppose we have these new divisions, okay, in r. What do they correspond to in xy? Well, they correspond to circles here. What are these division in theta corresponds to? Well, they correspond to different angles here. Okay, and so if we take, for example, this thing over here, okay, or here, this little square, it corresponds more or less, yeah, I'm sorry, to, let's see, it's 3 units up with the theta, so 1, 2, 3, and it's 3 units down from here, so it's 1, 2, 3, so it's more or less this stripe over here. Okay, so this unit is, when we sum it up, its actual area in the xy plane is this thing. And remember, we actually are interested in the area here, right? So here is a better graph that I took from a website that I will post a link to in the description. But in general, each rectangle in r theta, each rectangle here, is translated into some weird stripe, or we can call it maybe a polar rectangle in the xy space. We need to approximate how much is this area is equal to in regards to this area. So if here it's like a 0.1 times 0.1, how much is it here? Okay, and what we can do is, well, we can approximate it either by a trapezoid, by more simply by a rectangle. So even though this looks a bit like a trapezoid, we can say it's more or less, the more we go down, 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 and we take smaller and smaller dr d thetas, then it will look more and more like a square or a rectangle. And we can say, okay, this is a rectangle, and then just take this times this. Well, this, we know it's just the dr, right? It's just a small increment in r. But what is this? Well, this thing is actually an arc length, okay? We know that an arc length is equal to r times the angle. So if we have 360 degrees 2 pi angle, then the entire length, the entire circumference is equal to r times 2 pi. But if we have smaller areas and smaller angle, let's say theta, then it's just equal to r times theta. Okay, so this will be the r, okay, and it will be the same here, here, but this will be r up to this point times the theta. Okay, and you can see that when we go higher, when r is bigger, then this is bigger, and when r is smaller, this is smaller. We have to correct the integration area, so instead of dx dy, we will write r dr d theta. Now, to say that this is equal is not exactly correct. I will explain it later, but we just replace the dx dy by r dr d theta. Okay, so here you have an example, but you can pause the video and look at it. I will just move on. The polar coordinates were a special case of change of variables in 2D. And in the general case, what we will have is that we will have some integral, and we might say, okay, it's too hard for us. So we do some change of variables. We notice that we can replace f with some u and v, where u is a function of x and maybe also y, and v is a function of x and y. U and v are a function of x and y. We can get to the reverse transformation and say x is a function of u and v and y is a function of u and v. So the general formula will be that the double integral of fxy will be equal to the double integral of u and v, but we have to correct for the area of the u dv by multiplying with the Jacobian, where the Jacobian is defined to be the absolute value of the determinant of this partial derivative matrix. So we take the reverse transformation and we take the derivative with u and the derivative with v, and also for the y, we take the derivative of u, derivative of v, we take the determinant, and this is what it is. Okay, so again, the Jacobian only measures how much our integration area was changed. And the 1D case that we saw before is actually also a Jacobian, it's just a 1D Jacobian. And so because the function value doesn't change, we can, for simplicity, say that it's equal to 1. The only thing we have to change is, well, of course, the limit of integration might be different. The function value doesn't change, but we have to correct for the units of integration. So instead of the dx dy, we have to take the Jacobian determinant times the u dv. And again, we move from here to here, and we have some, this is the transformation that we did, but we can also look at the reverse transformation. If now we are here, okay, we sum here, we can't just sum it up, because if we sum it up in this case, well, it's 1 times 2 pi, and it will be equal to 2 pi, but this is wrong. We know that the area of the circle unit is pi, right? If r is equal to 1, then pi r squared is just equal to pi. And again, we have to correct for this. And the way to correct for this is remembering that each rectangle here is equal to some stripe here, and multiply by this stripe, by this deformation. Now I'm going to go into more details about why is this Jacobian correct? Why is the Jacobian capturing how much deformation happened to our little rectangles in the r theta or in the uv plane, where we actually do the summation, the integral. Okay, so if I already convinced you that we are moving from rectangles via reverse transformation to this deformed shape, then let's see why the Jacobian captures this new deformed shape. And what the Jacobian actually does, it does a linear approximation of this new shape. So instead of capturing exactly the new shape, it will capture some parallelogram shape here, which is a linear transformation of the rectangle here. This is not an exact area, but as the du dv becomes smaller and smaller, this linear approximation, this first order Taylor approximation, will become better and better, and in the limit will actually be equal. Okay, so we have, let's say, some initial points, u0 and v0. Let's suppose that it's mapped into this point over here. We want to see how much a small increase in u and a small increase in v, where is this mapped to? Okay, where is this point mapped to? Now, in reality, it will be mapped to here, but we will approximate where it is mapped to with a first order Taylor series. So we will get this point over here, And the same for this point. In reality, it will be mapped to somewhere here, but because we will use a first order Taylor approximation, we will get this point over here. And then we will want to calculate the area of this parallelogram. And the way we would do this is by taking the determinant of these two vectors, this and this. Okay, so first thing to notice is that a small change in u translates to change both in x and y. Because remember, both x is a function of u and y is a function of u. Okay, so we can look at each of these separately and approximate them with a first order Taylor approximation. And this is what the result will be. Okay, so it will be equal to the original point plus the change times the partial derivative of g with regards to u. Okay, and it's evaluated at the point u0, v0. And the same for h, we will get the similar thing. And so this new point, this point over here, where we just changed u by a little bit, it will be equal to the original point, okay, because this is just x0 and this is y0, plus some change of u times the partial derivative, the vector of partial derivative, where the first element is the partial derivative with regards of x with regards to u, and the second element is the partial derivative of y with regards to u, and these are evaluated at u0, v0. And similarly for v, we will get the same thing, only instead of a small change in u, we'll get a small change in v, and the partial derivative will be with regards to v. So we have now the vector of this, we have the vector of this, we have the vector of this. We want to find this vector, right, and this vector. Then we just have to subtract them, and we will get, so this is the first vector and this is the second vector. And now we need to find the area of the parallelogram that is captured between these two vectors, and it's equal to the determinant of these two vectors. And there's a few ways you can do this. One way is to look at it as a cross product, go to one higher dimension, use the cross product and get it. Determinant or the cross product of this, we will get it is equal to this, and this we can just call it the Jacobian. Another way that we can look at it is to say, okay, what is actually happening is a linear transformation of the du dv. Okay, so we took some point here and we did a linear transformation of du dv, and now it's some other form here. Okay, and so it's equal to the deformation of this transformation is captured by the determinant of the matrix that we multiply. So if the matrix that we multiply is this thing, we just need to take the determinant of this to see how much it's actually changed. And so again, we get to the same result, which is that the Jacobian, the determinant of this partial derivative matrix times du dv is the correction that we need to use. So a few notes. Well, we write this thing, but it's not exactly correct to say this. It's not that dx dy is equal to the Jacobian du dv. They are not equal by themselves. It's not that dx dy is equal to the Jacobian times du dv. They are only equal inside the integral. Okay, what I'm trying to say is it's not that dx dy, it's not that this is equal to some transformation times this. No, this is not true. So for example, if we look at the opposite, if we look at the rectangle in the dx dy, it's actually equal to dr d theta times 1 divided by r. And you could check this if you take 0.1 to be dx dy dr, equal changes in dx dy and equal changes in dr d theta. It's the opposite. And this is a thing that kind of bothered me, and I really had to lock down for myself. Okay, this is just a small thing that bothered me, and it's not really crucial. We can take, for example, again, the polar coordinates. So if x is equal to r cosinus theta and y is equal to r sinus theta, then the Jacobian is, if we differentiate with regards to r, we get cosinus theta and sinus theta, and if we differentiate with regards to theta, we get this and this, and if we take the determinant, we get this thing is equal to 1, and so we get back 1 r, which is what we wanted. Okay, and looking at change of variables in PDFs, if we define u to be some function of x and y and v to be some function of x and y, then we can look at the inverse transformation and then just correct the new PDF after we replaced the x and y with u and v by the Jacobian of u and v. And a few points to take into consideration. The determinant of the inverse of A is equal to the determinant of A inversed. So we can also, instead of using the Jacobian of the transformation u of v, we can use the Jacobian of the inverse transformation from x, y. So the inverse transformation is looking here and taking the partial derivatives with regards to x and y. So this is what I would think be the natural transformation, but actually in the Jacobian, you have to look always at the reverse transformation. So we can look at the natural transformation, which is, okay, if we define u to be some function of x, then let's just look at the partial derivative of that, but we have to take its inverse. So one example is to see, okay, if we look at we moved from x, y to the polar coordinates r and theta, then let's look what are the partial derivative of this, and it turns out it's equal to this. And if you develop it more, you get to 1 divided by r, but what we have to change is not 1 divided by r, it's its inverse r. Okay, so this is one point that is maybe useful to remember. Another point is that if the reparameterization is independent, so if u is not a function of x and y, it's just a function of x, and if v is not a function of x, y, it's just a function of y, then the opposite is also true. X is a function of u and y is a function of v. Then in the partial derivative matrix, we will have 0 and 0 here, and this will just be equal to the derivative of x with regards to r times the derivatives of y with regards to theta. One final point for this entire video is, of course, you can also generalize it to more than 2 dimension. You can go to 3 dimension and etc. And this is the form that you will have to correct for. So this was a long video, but I hope you found it useful. If you enjoyed, please leave a like and subscribe. See you in the next one.